Hello and welcome again to my channel. This is balancing of HVAC system part 2. In the previous video we talked about the types of balancing of HVAC systems, balancing valves which are used to make balancing in hydronic system. In this video we are going to talk about three main conditions required for each hydronic system to be balanced. If these three conditions are existing in any hydronic circuit, we can call this circuit is balanced. So what are the three basic conditions? The first one is the flow rate must be available to all terminals, even the furthest ones. This means all AHUs, all FCUs must have water flow running inside the coils. The second condition, the differential pressure of the control valves must not vary excessively, especially they should not exceed the maximum and minimum levels of work. The last condition, flow rates must be compatible at the system interfaces. This means overflow should not be existing or underflow of the coil. So let's go how to obtain the three basic conditions for balancing. The first condition, the design flow rate must be existing in all terminals, even the furthest one. The key to maintain this condition by dimensioning the plant carefully. Okay, so this means we have to size the pipes of the chilled water carefully in order to have the required flow. We have to select the terminals carefully in order to give us the required capacity. If this existing, the circuit will be balanced and the flow will be existing in the terminal. So for this condition we have three cases. Case number one, constant flow rate distribution system. In a constant flow rate distribution system, the three-way control valve is calculated to generate a pressure drop at least equal to the design pressure drop in terminal. This means a control valve with an authority of at least 0.5 is essential value for proper regulation. Practically, the pressure drop on the control valve must be the same of the downstream pipe. If the pressure drop in the pipe plus the pressure drop of the control valve is 20 kPa and the differential pressure available delta H is 80 kPa, then the 60 kPa difference must be removed by static balancing valve. That means this static balancing valve is essential in this position of the circuit, otherwise the circuit will be unbalanced and the flow will go to the bypass line here, and there will be underflow here and the system will be unbalanced. I mean, the terminal will be underflow water here and system will be unbalanced. Situation B, variable flow rate distribution systems. In variable flow rate distribution system, the insufficient flow rate problems occur basically when high loads are required. There would no justification for balancing a system with two-way control valves on the terminals, since these valves are designed to modulate the flow rate to the required level. Hydronic balancing should therefore be obtained automatically. However, as soon as the proportional valves begin to close, the differential pressure can increase considerably, generating noise and regulating disturbance before the pump can react. Trying to avoid overflows this way will simply make the problem of an inadequate flow rate worse. Specific devices are to be added in the circuit in order to give balancing for the system, such as differential pressure control valves (DPCV), which are specially designed to handle this situation. DPCVs set the differential pressure to the desired level. This level should be adequate to obtain the design flow rate in the furthest pipes while not exceeding the maximum value associated with the valve actuator combination based on the maximum force of the actuator itself. And the last situation C, which is start-up. In variable flow rate distribution systems, start-up after each shutdown represents a delicate operation as most control valves are activated while fully open. This situation generates overflows that cause excessive pressure drops in some parts of the pipeline network, while not supplying the terminals of less favored sections of the plant. Disadvantaged circuits will not reach a sufficient flow rate until the privileged rooms have reached the thermostat set point, assuming the set point has been selected in a reasonable manner. This allows the control valves of said circuits to start working properly. Startup is therefore difficult and takes longer than expected, as shown in the diagram. This results in heavy energy consumption. In addition, uneven startup makes management by a central controller and any form of optimization practically impossible. Second condition: the differential pressures of control valves must not vary excessively, and more importantly, they must not exceed maximum and minimum levels of work. The variable flow rate systems are becoming more and more popular, especially for the advantages they offer compared to constant flow rate systems, such as: number one, reduce pumping costs; second, retain temperature, which is minimized in heating systems and maximized in cooling systems. For this condition, we are defining circuit compound characteristic. The circuit compound characteristic consists of actuator characteristic, which is the relationship between the control input signal from the controller to the actuator and resulting valve movement H. Second, valve intrinsic characteristic. The intrinsic characteristic of the valve, which shows the relationship between the valve opening and the flow, and its flow coefficient Kv value, depends only on the mechanical configuration of the control valve. Third, terminal characteristic. The terminal characteristic can vary greatly depending on shape, size, temperature, but it definitely nonlinear. Valve authority. The valve authority is measure of differential pressure variation through a control valve during operation. The flow rate through a control valve depends on the differential pressure through the valve and its KV value. The KV value is given by the intrinsic characteristic of the valve at each of its opening levels. If differential pressure is constant during operation, the KV water flow rate would be completely linear. The relation between KV and the water flow rate will be definitely linear. However, in variable flow rate systems, the differential pressure varies during operation, which means that the relationship becomes more or less nonlinear. So as we see here, this is a circuit, HYDRONIC circuit. We have the balancing valve, which has the actuator, the valve, and the valve authority, and the terminal characteristic. So here we have actuator characteristic, which is linear, mostly linear. Here we have the valve characteristic inherent, which is parapolar formula, valve authority effect here, and terminal characteristic. All together will be given the circuit compound characteristic. Valve authority, the magnitude of nonlinearity is expressed by valve authority. Valve authority is delta PV design divided to delta PV shut. That means when the valve is fully open, design flow, and when the valve is fully shut. So all of our concentration to calculate the beta here, authority, is the relation inside the valve itself. So it is the valve authority to allow the flow or to stop the flow. So this relation, this formula, it is if the valve is fully open, it will be vary from 1 to 0 or 0.1, which means that the valve is fully closed. There is another definition for valve authority which related to the circuit itself. So the beta is delta PV design divided to delta H design. Minimum, it should be delta PV design divided to delta H maximum here. This delta H design or maximum. So this is the other definition of the authority. The ideal situation is represented by the circuit characteristic which with reference to the design authority of the valve considered corresponding to a situation of all control valves of the system are kept completely opened. So this is the best case. The worst case, the worst scenario would be a circuit characteristic with minimum valve authority when all other control valves are kept completely closed. Here the worst, less authority, that means worst case. Basic principles of hydronic design. We have three basic principles to take into consideration. The design flow rate must be obtained with the valve fully open under design condition. Second, to facilitate regulation, the valve characteristic must compensate for the nonlinearity of the terminal. Last, to maintain a favorable circuit characteristic, the valve authority should not be too low. To prevent valve authority from deforming the circuit characteristic too much, the lower values of design authority and minimum authority must be. For design authority, it should not be less than 0.5, and for the minimum authority, it should not be less than 0.25. The design authority of control valve must not be less than 0.5, and this means, in practical terms, that the design pressure drop through the fully open two-way valve must be at least equal to half the differential pressure available on the circuit under project conditions. The purpose of this first guideline is to make sure that the circuit characteristic in the best conditions has an almost linear pattern, assuming that the control valve has been chosen with an appropriate intrinsic characteristic. This we can get it here in between this and this lines here. We can get the 0.5 almost in the middle of these two curves. The second condition, that is minimum authority is not less than 0.25, sets the lowest level of the circuit characteristic under the worst operation condition. Clearly, this restriction is the most important because it actually defines the limit for the stability of the regulation. We cannot stop the valve 100%. We can keep here the worst case. We cannot reach to the worst case, so the 25 will be here after this curve. So the 0.5 will be after this curve, and 25.25 will be after this curve. So the valve life is running between these two figures. In addition to carefully selecting the control valves, there are other measures to be implemented during design to avoid a low authority. Avoid large pipe pressure drops. Use variable speed pumps. Use differential pressure control valve DPCV when required. Now, third condition, flow rates must be compatible with system interfaces. In many systems, the installed power exceeds the required maximum value by more than 30%, but the distribution circuits still do not receive enough power. The power produced by chillers simply does not reach the cooling circuits. This problem can be particularly critical in systems with multiple chillers working sequentially. The reason is generally due to a lack of compatibility of the interfaces between the production system and the distribution system. So, how to avoid such problems? The main problem is the incompatibility between the interface of production and the distribution system. There is no compatibility between the distribution and the production circuits. So how to avoid this problem? This problem can be avoided first by hydraulic interactivity. Hydraulic interactivity occurs between multiple parallel units that share a common resistance, like these two chillers here or boilers. They are sharing these 2 points. They are sharing this point and this point. So they are doing the same. This point has the same resistance for the same this chiller and this chiller. Any variation of the flow rate through a single circuit affect the others. The greater the shared resistance, the greater the interactivity between the circuit. The two chillers create a shared resistance for the distribution circuits, and therefore any flow rate change in a circuit will naturally affect the flow rate in the other. In addition, variable flow should run through boilers, but this situation is not acceptable for standard models. Second, bypass separation. A low pressure drop bypass line here, or even typically hydraulic separator between production and distribution, solves these interactivity problems. However, the compatibility between production and distribution flow rates must be ensured. Bypass between A and B keeps the differential pressure between these points close to zero, and there will be no interactivity between the circuit or between the chillers. Therefore, there will be a constant flow rate in each boiler, and there will be no risk of freezing in case of the chiller. Bypass avoids any interactivity, but since the pressure drop between A and B is not existent or very low, a secondary pump is required. However, solving interactivity problems with a bypass creates compatibility issues unless correct measures are taken. In this example here, the secondary pump is oversized and the distribution taken up 150% of the flow rate, while the production is only 100%. The production units provide only 100% of flow. The difference amount of 50% here has to go through the bypass from B to A, creating a mixing point not controlled between supply water and return water in A, making it impossible to reach the correct delivery temperature. In the heating example, this example is for heating. Okay, so the delivery temperature will be only 73. This is for cooling and this is for heating. The delivery should be 73 instead of 80 degrees desired, because here is the desired and here is the result. So this problem, because of adding the pump, we reach to undesired conditions for cooling 8 degrees and for heating 73 degrees. So how to solve the change condition issues? Shall we take a corrective action to increase the pump? Let's try to increase the pump and see what will be the result. What would be the result? As we are seeing here, increasing the hydraulic head of the distribution pump could be thought of as first attempt to solving this problem, but it actually only worsened the situation, because as you see here, the desired condition was 8 and now it is 9, so it is increased. The original cause of the problem is an excessive secondary flow rate, so and even here also we have secondary flow rate excessive, 100% extra. So an even higher delivery flow rate will only increase flow incompatibility and therefore mixing. The delivery water temperature will further decrease in heating and increase further in cooling, in this case from 8 to 9. Next, add power from the primary circuit. Shall we think of adding another chiller in order to get the desired temperature? Let's see this situation. Introducing extra power output through an additional unit can solve the problem of incompatibility, but at the very high cost of unnecessary installation, because we added another chiller will be another cost. So adding another 50 flow rate will be aligns the flow rate between production and distribution and make it possible to reach design delivery temperature. Here 6 degrees, we required 6 degrees and we are getting 6 degrees, but with an excessive flow rate in distribution. So we have 150 excessive flow here because we added 150 and we deliver 150 here. Instead of 100 only, we added another 50, so the result will be overflow. But with an excessive flow rate distribution, this system created will be characterized by high cost, first in installation and then in operation. Since normally oversizing is in energy production reduces efficiency. This actually will be reducing the efficiency. So this solution also not acceptable. Let's go to the next solution. Maybe we can find the solution. Change the set point. Change the set point. Instead of 6 degrees, make it 3 degrees. If we decrease it, if we decrease the set point of the production unit, it can compensate the incompatibility issue, because we need the condition, we need 6 and we get 6 here degrees as a result in the distribution here. But this actually will provide us the correct temperature, while the result is drastic energy costs in the plant, and therefore it is not recommended solution, because it is energy waste. This solution is energy waste because the chiller is required to give you 3 degrees. That's why you need to make the set temperature as a 3 is energy loss. Last solution, which is the preferred one, balancing the flow rates. The incompatibility problems described above depends only on overly high flow rates in distribution. It is inevitable that the correct measure of an intervention is to equilibrate production and distribution flow rates by balancing. By doing so, there will be no flow in the bypass line, and so the correct flow rate and delivery temperature will be transferred from production to distribution. This approach is not only valid between production and distribution, it should be used in any system interface or where different circuits are in contact with each other. So for balancing, this circuit is unbalanced because there is bypass, 50% of the flow going through bypass. So if we added balancing valves here, there will be no flow in the bypass line and the system will be balanced, and it is the preferred solution. Finally, we get the solution by using balancing valve. At this point, we completed part 2 of this study. The next session will be balancing methods and will be coming to you soon. Please feedback in the comments. Kindly subscribe in my channel, like this video and share. Thank you.